Hi everyone, welcome to my talk. Today I'm going to talk about quantum algorithms for convex and non-convex optimization. First, the problem that we are going to discuss about today is a function f define an n-dimensional space R to the n and also maps to the real numbers. And the goal is to find x and minimize the corresponding function f. Such kind of optimization problem is a core topic in math, in theoretical computer science, in operations research, etc. So from the computer science perspective, this is also of significant interest in general, I think especially for the perspective of machine learning, because training a machine learning model is just equivalent to optimizing a certain loss function. So I think this conference is mainly a theoretical computer science conference, so I guess we are probably very interested in provable guarantee of solving such kind of optimization problem. So a very natural question to ask is what kind of provable guarantee can be achieved for solving such kind of optimization problem. So probably this is difficult in general, but we want to start with some very nice cases and examples and see, for instance, for some special cases, we really want to give a good algorithm, a good quantum algorithm for this topic. So the first class that we are actually going to study is the convex optimization problem. So this is one of the most important classes of problem that can actually be solved in polynomial time. So if you want to think about what is the most general kind of convex optimization problem, it will probably be something like this. So you just want to have two constraints, whereas the first constraint is that the function that you're going to optimize with is a convex function f. And also on the other hand, maybe typically for a lot of optimization problem, you have constraints. You will assume that the x is constraining a certain convex body C here. So the only two assumptions here are the fact that f is a convex function and the set C here is a convex set. Okay, so having these two very general assumptions, what can we further do to characterize a corresponding algorithm? I think we should be given the ability that you can maybe get some access to the function f and the convex body C, and this is typically given with two kinds of oracles. So for the convex body, it is typically given to be an oracle called the membership oracle. That is to say, you give me a certain x and then tell you whether this x is inside the convex body C or not. Another very common oracle is the evaluation oracle. That is basically, you give me an x and then tell you the corresponding function value at x. The goal of the convex optimization problem is that given a certain parameter epsilon for accuracy, you want to return a certain tilde x such that the function value of the tilde x is very close to the minimum. It's like epsilon close to the minimum of f in this convex body. Okay, so I think this is probably a well-known or a folklore result, the convex optimization, that basically set kind of tilde x can be found in polynomial time. For instance, using like a very traditional method of the ellipsoid method, or maybe using some other methods like the cutting plane methods, interior point methods, etc. Because of the importance of this convex optimization problem, I think experts in theoretical computer science has really been pushing forward to understanding the best possible complexities. And currently, the state-of-the-art result by Li, Sidfor, Wampala in code 2018 uses quadratic number of queries to the membership and evaluation oracles, and the whole algorithm runs in time n to the 3, cube in n. So I think my talk is basically a quantum computing talk. So the main topic here we are going to ask is that whether we can give a fast quantum algorithm for this convex optimization problem. By the first hand, we should probably be given some ability like to access the convex problem quantumly. So here, the two assumptions that we are going to make is to have the quantum version of the membership oracle and the evaluation oracle. So specifically, the quantum membership oracle is to give you the ability to ask membership in superposition. So you see like it's basically a unitary oracle that maps the quantum state x0 to the quantum state x SCX, where the SCX is just the indicator function that equals to 1 if the x is inside the convex body or equals to 0 otherwise. And similarly, we have a quantum unitary oracle OF, which is the quantum evaluation oracle that can map the quantum state x0 to the quantum state fx. So as you can probably see, the only extra ability that we assume here is to have the access to both oracles in superposition, and we want to ask whether we can get faster quantum algorithm for this general convex optimization problem. And the answer is yes. So the main result that we actually gave for general quantum algorithm for general convex optimization is that we only use a linear queries to both oracles, both the membership and evaluation oracles, such that we can solve the whole problem. And actually, similar to the classical state-of-the-art algorithm due to Lee for one Pella, we also use like n to the 3 additional arithmetic cost. So how should we understand this result? I guess it has two sides. I think the good side is that this is the first non-trivial quantum upper bound on general convex optimization problems. But of course, since we have been showing like lower bound in square root of n here, we are probably been teaching a lesson that is impossible to get generic exponential quantum speedup of convex optimization. I think exponential quantum speedup is in general the story that we like very much. For instance, like the shortest algorithm for factoring, but we basically show that this is impossible for the general convex optimization problem. So I think today, maybe let me very briefly highlight about the algorithm part and give you some inspiration about how this is achievable only using linear number of quantum queries here. So the strategy that is actually used in the Lee for Guampala paper is that you want to consider different kinds of oracle reductions. So the OPT is just the optimization oracle that we finally want to achieve. And in the middle, there is an oracle called the separation oracle, which is actually stronger than the membership oracle. And actually, it looks like this. So assume that you have a certain convex body, and basically, maybe you have a certain point in this whole region. If a point is inside this convex body, it just tells you that that it's inside. But if the point is outside the convex body, for instance, like this point, the membership oracle only tells you that this point is not inside the convex body, but the separation oracle gives you more information. It requires that you give me like a separation hyperplane. So basically, this separation hyperplane that separates between the convex body and also this point here. So the main question here is that I think it is a poor result that if you have a separation oracle, you can solve the optimization oracle only using like tilde O of n queries. So just like a ellipsoid method. So basically you have separation oracle like this. You can each time cut the convex body, cut the convex body, cut the convex body, and you're only using like n iterations. The volume of the still feasible region will decrease exponentially fast. And actually, overall, it's only like a tilde O of, and where the tilde O here means like polylogarithmic factors. You can actually solve the corresponding optimization problem. But the main question here remains is about the reduction from the separation oracle to the membership oracle. And the main contribution that is shown in this Lee for Guampala's paper is that this reduction also takes a linear queries classically. So in total, like it costs like quadratic n to the 2 classical queries for solving the optimization problem. So roughly speaking, what is the idea that is used in the Lee for Guampala's paper? It is something like this. You consider like the boundary of the convex body and also this point. So because you have the membership oracle, basically, for instance, you can do like the binary search along the boundary here. You will roughly speaking get an idea about what the boundary is and actually like these points. So what is a good separation hyperplane? You can basically just consider such kind of distance function between this point outside the convex body to the points on the boundary of the convex body. And maybe you just do a derivative, and this is going to be a tangent line of this convex body, and actually it perfectly separates between the convex body and the point here. So actually, we follow this idea due to Lee for Guampala, but we give an even much stronger reduction that basically the quantum separation oracle can be reduced to only like polylogarithmic queries to a quantum membership oracle. And in total, you can see that if this is tilde O1 and this is tilde On, then basically the whole reduction takes only tilde On of quantum queries. So how do we achieve this? So this is achieved basically by constructing a quantum subgradient oracle for the distance function. So let me highlight the idea here. So this is not something originally given by us, but originally given by Stephen Jordan on a paper about quantum algorithm for gradient computation. So having such kind of quantum evaluation oracle, you can basically, it's a standard trick to prepare like a quantum state to prepare the function value into its phase. And this is a standard technique called a phase kickback. So after having the phase kickback, you want to maybe put this into first order Taylor approximation. And you can see that the first order Taylor approximation have such kind of form. We basically only remain the Taylor approximation up to the first order. So Another way that you can look at this fact is that if you want to take the summation, if you, for instance, you put a uniform mesh around a certain point that you want to compute this derivative, you just like construct a corresponding uniform superposition in such kind of sense. But the important thing is that if you look at such kind of Taylor approximation, if you do such kind of summation, actually the thing in the face here, it actually you can just you can rewrite this as a tensor product form of such kind of summation. So you can actually put all the partial derivatives together into such kind of a tensor product, and actually the superposition uniform, the summation of the uniformization will go outside. So what is the main inspiration here? And I think this is basically based on important quantum technique called the quantum Fourier transform. Is that basically if you have all these kind of things in phase, the quantum Fourier transform can simultaneously extract all the information of the phases here on all the n systems. So basically apply the quantum Fourier transform. All the n coordinates will reveal all the information of the partial derivatives simultaneously. So this quantum Fourier transform technique is very powerful. It's the main technique behind the Shor's algorithm using a specific very important subroutine called period finding. So here, basically in general, as long as you have something in this kind of imaginary exponent, you can, and also in this kind of tensor product form, you can extract the information only using one application of the quantum Fourier transform. So this is like a very roughly speaking the idea of our algorithm behind of our quantum algorithm for convex optimization. And as just a very briefly mentioned, so basically the reduction from the separation to membership is only polylogarithmic then, and together with like we just trick the second part, I mean from optimization to separation oracle, just using like the vanilla version of the ellipse-point method, but that can still in total give a quantum algorithm that takes tilde O of n quantum queries. Okay, so this is a brief highlight about this result. And actually, this result has been there for about 2 years, so this is not the main focus of today. So the main focus of today is that we want to move forward. In general, we want to give a better understanding, and I think this is probably not the end of the story, and we can probably do more. So in retrospect, what do we want to think about, and actually, what is the thing that we can actually improve further for this line of research? I guess, especially when talking to the machine learning community and to look at their recent advances, and I think, I think there are really actually two concerns that we want to be careful about. So on the one hand, I think, especially in practice, the loss function of the vast majority of machine learning models are typically non-convex. So for convex functions, you will probably get something like this. This is really a great landscape, and actually, especially for convex functions, one very significant simplicity is that the convex functions only have a unique local minimum, and actually the unique local minimum is just like the global minimum. But in general, for non-convex functions, what makes the thing really complicated is that you can maybe have such kind of landscape, and there are just so many local minima, and you probably have no idea about where the global minimum is. So this really makes the problem complicated, but actually, this such kind of landscape is the landscape that we typically encounter with when we do when we train the corresponding machine learning model and optimize this corresponding loss function. Another main concern that is actually raised commonly considered in these days machine learning is that we are actually dealing with a very large dimension. Usually the dimension is more than say 1 million. But sometimes, I think typically for many cases, the machine learning training is robust. And we can actually tolerate a reasonably large epsilon. So for instance, maybe at a scale, maybe we say that n is 1 million, and epsilon is maybe only thing like 0.01, it's like 1/100. So you see like their scale is quite different. But if we have like a classical algorithm of n to the 2 or quantum algorithm with cost n, that is so large compared to the dependence of epsilon here. So actually, speaking of provable guarantee, I think these days, especially from the community of theoretical machine learning, maybe we do want to pursue algorithm with cost like, not we want to have the log to be on the 1/epsilon side, but we really want to have dimension to be small. That is, in general, we want to pursue for algorithm with cost maybe poly of log n, and also 1/epsilon here. So maybe I think it's just impossible to get logarithmic dependence for both parameters. But for the latter case, I think it is more important. And these days, such algorithms are typically called almost dimensional free methods. So what is one of the most typical dimension-free methods? It is the gradient descent. That is basically from a previous iteration, assume that you have certain xt here. You want to compute this gradient, and maybe you want to have a set up a certain step size, and you want to move forward in this kind of sense. So what is the good thing of the gradient descent? Actually, it has relatively good theoretical guarantee. So if the function is not too bad, for instance, you assume the function to be an L smooth function. So basically the gradient has such kind of L Lipschitz. Then basically using like roughly speaking like L over epsilon squared number of queries, you can actually get to a point where the gradient is very small. So because this is like the gradient is like a first order information of the function here, this is typically called like epsilon approximate first order stationary point. The main question here is that, is this good enough? So this gradient descent algorithm is so simple and actually give you a very good performance in the first order. But we want to ask that whether this suffices for real applications. So maybe let's look at an example like this. So this is just a non-convex function, the landscape figure that I used just now. So what are the main like trouble that actually we will encounter when we train like a machine learning model with a loss function like this? There are some bad things called saddle points. So for instance, if you just consider gradient descent, maybe from this step, you'll probably do go like this direction, go this direction, go this direction, and you will be trapped at a saddle point. So at this point, you see like its gradient is actually 0, but this is not like something you really want. I mean, you will be trapped here, and I think you really actually want to find some way to further step down, but this does not allow you to do so. And similarly for this point, you see actually for this right on the saddle, the gradient is actually exactly 0, but you cannot make a further movement. So this is actually one of the most troublesome property of the gradient descent idea. And I think in practice, we don't want such kind of saddle points, which makes us unhappy, but we do want to get something much better. We want to get local minimum in this of sense where actually it is really a locally it is minimal compared to like its neighborhood. We really want points like this. So, and also this is just like a very high level intuition, and I think I want to give you some common facts that typically appears in many machine learning problems. So actually, although it's called local optima, but for many cases, like maybe for instance for tensor decomposition or for matrix completion, for a lot of important problems for machine learning, there are such kind of landscape results in theory showing that in most cases, local optima is actually not that bad. It's actually quite close to the real value of the global minimum. But also on the other hand, such kind of saddle points and maybe even some very bad things like local maxima, they can actually give highly suboptimal solutions. But this is the bad thing. The unfortunate thing is that it is also quite common that the number of saddle points are large. In general, they are ubiquitous in the whole space. And I think in general, we are probably not too ambitious because in general, finding a global minimum of a non-convex function is an NP hard problem. So what can we make a conclusion about these common facts of that we actually encounter in machine learning is that we really want to escape from saddle points, but we are probably satisfied with reaching like an epsilon approximate local minimum. So local minimum is really like a second order property because you see you don't want to have any direction that is whose hashing has like very negative eigenvalues. So here, if you want to consider some epsilon approximate local minimum, it's basically you want to get a promise that both the gradient is small, but also like the second order, the hashing information is close to a positive semi-definite matrix. You can probably tolerate a small bound like a minus the square root of rho times epsilon, where the rho is the Lipschitz constant for the corresponding hashing information of the function f here. So this is a very important problem these days in the study of learning theory. And I think this is the main focus that I'm going to discuss next. So how about the previous results? So previously there has been, especially recently, there has been a significant interest, and you can see like these are all very recent papers. So actually it is quite like a folklore result that if you want to reach like a second order local minimum, you can probably just utilize the second order information. So for instance, you have a hashing oracle, then probably you can using some type of Newton method, you can give a good promise that you can actually reach a very good local minimum. But actually the main issue that is a little troublesome is that the hashing matrix is an n by n matrix. So you see like this, if you want to store the whole hashing matrix, that cost is already n squared. So that is actually comparable to, for instance, in the convex optimization part, similar to the cost of leases for one pallet. So in general, like this n squared, the hashing information is just too expensive in practice. And we really don't want to have such kind of things. So a main focus these days, especially in machine learning research, is that we want to make simpler and simpler oracles. So for instance, the hashing is very important. It's very important, but also it's very expensive, like the matrix and square cost. But maybe we want to consider something slightly simpler. It's like a hashing vector product, which also commonly appears in the way of training many machine learning models. But I think the simplest oracle that classical people really care about is the gradient oracle. This is basically because when you train a neural network, so a neural network, you have like this kind of backward propagation. The backward propagation directly gives you the gradient information. So this is one of the most important reasons that they actually want to consider simpler and simpler oracles. And especially the gradient oracle is one of the most important oracles that classically machine learning people care about. So as you can see, like in the movement from the hashing oracle to hashing vector product and finally to the gradient oracle, like the complexity is actually changing, and actually the state-of-the-art algorithm can give good epsilon dependencies, like lower epsilon to the 1.75, but unfortunately it's slightly further compared to like dimension-free methods. Although it's still polylog, but the log dependence here is log n to the 6, which makes the algorithm quite expensive. But I think classically, this is really, as I will later mention, this is really some technical difficulty that is not very easy to get rid of. So the main focus of today is that we want to take a closer look at this problem of escaping from set points, and we give a much faster quantum algorithms. So using the quantum evaluation oracle, we can actually further simplify the oracle. We don't even use like the gradient oracle, but we only use quantum evaluation. It's because like the gradient has n coordinates, but evaluation is just like one coordinate, just like one real number here. So the oracle, although being quantum, we make the information. So the gradients, because it's like the first order derivative, is typically called the first order oracle. We can actually improve from the classical first order oracle to a quantum zeroth order oracle. And actually this is also a significant simplification in the definition of oracles. But also on the other hand, you can see the query complexity. We improve the classical large dimension dependence log n to the 6 to log n to the 2. And in other words, we can actually achieve like a cubic quantum speedup in terms of n here. And also, as I just mentioned, we use lower order information than the classical algorithms. Okay, so let me highlight the brief idea behind. Let's first begin with the classical algorithm and then introduce the advance that happen in our quantum algorithm. Okay, so the main idea is that you can maybe back to imagine the landscape of this non-convex function that you are going to be trying to set a point. So maybe you can consider such kind of things. Maybe you want to bring some randomness inside. So assume that this is maybe let's zoom into a specific set of point, and maybe let's consider, maybe we begin with this point. If you do gradient descent, you will go down, but unfortunately you are going to be trapped at this set point. And maybe for some other routines, that maybe you start from this point, but you will also get very close to the set point, which is somehow a little bit difficult to get rid of. But the idea here is we want to bring into some randomness. So for instance, maybe we can draw a ball here, and we can maybe shake around this ball. I mean, we don't really want to focus on the set point, but we somehow like shake, maybe follow some distribution and inside the spell, and we can, after, for instance, assume that we have been sampling this point, we can check actually this is really good. And if you do gradient descent, it will go down and actually really escape from this kind of set point. So this is really good, and such kind of perturbation idea, and you can see intuitively you can see how it works, but there are some technical details that we should really get clear with. So for instance, about this kind of perturbation idea, you want to be careful, because if maybe we call this radius to be the perturbation radius. If this radius is too large, for instance, it is as large as this, then with a quite reasonable probability you actually quite trace back a lot, which is really not very good for the perspective of optimization. But also on the other hand, if the radius is too small, it is very small like this, then it does not move a lot, and actually you probably you need to do a lot of gradient descent steps to actually get rid of the set point. So the choice of the radius of the perturbation is really something quite intricate here, and you want to be careful about. And also, on the other hand, a main question here is that what is the most efficient approach that we can make the perturbation? So what kind of distributions that you probably want here? And also, so in general, I think I'm mainly talking about gradient descent, but if you are familiar with the theory of optimization, there are other kind of methods. So can we actually improve on the gradient descent part per se? So the answer that actually in the classical state of the art due to Jin et al. Is that is like this. So for the gradient descent part, we use an alternative called the Nesterov accelerated gradient descent. So this is going to this is actually given the best theoretical guarantee for smooth functions. And actually, in our research, we always study smooth functions, because if the function is not smooth, it does not make any sense to talk about like the second order information like set point, etc. So the Nesterov the accelerated gradient descent (AGD) is basically something like this. It is like actually like a momentum-based method that you have like xt, and also have a momentum vt here that you're actually alternating. You are going to alternating between like the gradient descent step and update of the momentum information here. So I'm not going to introduce about the AGD here. This is really something mature in optimization theory, and maybe you can actually look at standard textbook. But this is really like a standard replacement of the original gradient descent. So the most important thing that directly relates to the setup point, as you may see, is like this perturbation. So how you are going to consider perturbation? So actually, what is happening in the classical state of art work of Jin et al. Is that if the gradient is small, it's just like you're going to make a detection. If the gradient is large, then it means that you are moving fast. You don't have to get worried. But if the gradient is small, say it's smaller than epsilon, and there has been no perturbation added in a while, say log n steps, you want to perturb by a uniform distribution above radius like epsilon over log n to the 5. So why log n to the 5? This is really something from calculations. There is no like direct intuition for that. But it's just that in calculation, you want to balance different things, like the thing I just said, the radius cannot be too large, nor it cannot be too small. So there's really somehow it's a little bit artificially chosen contrived value, but actually this can make the proof work. So especially this actually follows some idea from classical mechanics that you can actually characterize the dynamics by its corresponding Hamiltonian. So you have like the function f. This you can regard this as a potential of a certain particle, and this can be regarded as the momentum part. So actually, you can see you can actually prove it is actually proved in the paper by Jin et al. That the idea of the perturbed accelerated gradient descent takes like log n steps to decrease the Hamiltonian of the problem by 1 over log n to the 5, and the convergence rate is like 1 over epsilon. Convergence rate in epsilon is like 1 over epsilon to the 1.75. So that is the reason why the total cost is like log n to the 6 over epsilon to the 1.75. So the main question here, and actually you can probably see here, is that this perturbation is the idea is simple and actually it works, but the dimension dependence is so large, and maybe we want to ask whether we can improve on this. So what is the main intuition here is that, especially we want to, the main question here is in general about escaping from set of points and how we are going to escape from set of points. Like, can we use some other things other than perturbation, and especially under the quantum sense. So maybe if you in general think about this from a quantum physics perspective, what is the main inspiration here, and what is the motivation? I think this is quite similar to the idea called quantum tunneling. So what is the quantum tunneling? Is that if you consider the evolution of quantum wave equations, it can actually get rid of some hills like this. So for instance, you have a classical physics, you want to go to the other side of the hill, you have to climb through the hill, and this is probably really laborious and really costs you a lot. But the evolution of the quantum wave equation, you can actually tunnel through it, and actually, for many cases, you can get to the other side with a quite non-trivial probability. So can we actually take use of the idea of quantum tunneling here? And this is actually our main contribution here, that we make the idea algorithmic using quantum simulation of the Schrödinger equation. We just use the most standard version of the Schrödinger's equation because we have the function f here, and we have the quantum evaluation oracle. We just put it there, but we want to evolve the corresponding Schrödinger equation and see what is the phenomenon for the problem escaping from set of points. So basic assumption is that for Schrödinger's equation, especially when we are near a set point, the function can be well approximated by a quadratic function. So So after having an assumption of quadratic function, this really, because having this kind of quadratic thing, it really reminds you of the Gaussian distribution. So here we just assume that the initial wave equation that we are going to use is a Gaussian distribution. It's not like classically this kind of uniform distribution above, but instead we consider Gaussian distribution. So if we have such kind of Gaussian distribution under quadratic field, we can actually solve the corresponding partial derivative equation, the Schrodinger equation, analytically, and you can get a promise that the evolution of Gaussian quantum wave equations are still Gaussian wave equations, but the variance of the Gaussian wave equation is changing. So if the potential lambda it is defined by a constant lambda times the quadratic term. So if the lambda is larger than zero, you can see that this is at most a constant because cosine is at most 1 here. So this is at most a constant. When lambda equals to 0, this is a quadratic polynomial term here. But what is really interesting is that if the lambda is smaller than 0, you see that this is actually exponential decay, and actually it really disperses very fast along the direction because the variance is actually increasing exponentially fast. So this is the main motivation that actually behind our algorithm. So actually you can make analysis like this. So basically we want to decouple the directions of the hashing. So we want to focus on the most negative, the directions of the most negative eigenvalue and its corresponding eigenvector and the else. So if we are actually at a saddle point, we know that this most negative eigenvalue, actually it should be quite small. So you have this kind of threshold of this kind of epsilon approximation. So this lambda here should be smaller, should be smaller than that. But that, as I just mentioned, this has the phenomenon of the exponential dispersion for evolving a Gaussian wave equation. And actually, we can really borrow such kind of fact. And actually, you can see if you are near a saddle point, and then, as I just mentioned, this eigenvalue should be smaller than minus square root of rho times epsilon per the definition of a saddle point. And actually, because the dispersion is so large, even all the other directions go backward. You can actually still, with high probability, the function value still decreases much. So what is the intuition here? So assume that we look at this specific saddle point. So assume you are at a certain point here. So we assume that maybe all the other directions, the eigen directions are positive. Maybe assume that totally there are something like this. But because like this dispersion is so fast, it's just like you consider corresponding quantum simulation and you just measure the state. It's just like the variance so large that with high probability you're going to decrease a lot in this direction. And even if you trace back in all the other directions like this, you're finally still going to move along this direction because this is like the summation of vectors. You can see that this is still relatively good for the purpose of escaping from saddle points. So this is only the perturbation steps, and how does this combine with gradient descent? So after having this lemma in our paper, we can actually show the idea like this. So actually, we have two algorithms here. So the first is a gadget called quantum simulation. It's just that we begin with like this R0 is just like a scaled version for the original Gaussian wave equation for the normal distribution. So we are going to evolve such kind of Gaussian wave packet, and we put this into the potential field F with the Schrodinger equation I just mentioned, and evolve for a certain time TE here. And after evolving for this time TE here, you can see it's going to be a distribution in the whole space. We just measure it. So it's just like a direct replacement. We are not using classical perturbation anymore, but we use the quantum simulation to replace the classical perturbation step. And for instance, you put everything back to the algorithm. It's just like we just do the gradient descent. It's just like similar to the idea of the classical algorithm. You're only get warned if the gradient is small. But if the gradient is small, you don't do the classical perturbation. This is actually quite the quantum part. Actually, you just do the quantum simulation part to get rid of the saddle point. And actually, we can, in our paper, we prove this proposition 2.1 that actually give quite good theoretical guarantee for the overall quantum algorithm. So the remaining question is that we here assume the ability to simulate the Schrodinger equation, but what is the cost of the simulation per se? So this actually really go back to like previously quantum works mainly on two sides. So on the one side is quantum work for solving differential equations, especially for solving partial differential equations, and we actually take a closer look at this quantum PDE solver of the recent paper by Charles et al. And on the other hand, this is actually quite motivated by recent works on quantum simulation. So how we are going to combine them? So when looking at this quantum PDE solver, actually discretize the whole space, but in general, it's not very easy to manipulate the continuous space. We are going to make a discretization of the space using an idea called the finite difference method. And actually, by finite difference method, you are just going to put the whole space into grids with a certain side length, maybe a certain side length A here. In that kind of sense, this kind of partial derivative, the nabla square, is going to be approximated by Laplacian matrices, because as you can see by this very simple fact about like the value that is going to change in the second order partial derivatives. So after having this kind of change, you can see this just corresponds to like the Laplacian matrix of the graph of the grids. And actually, on the other hand, all this kind of F here is actually going to be changed into some certain matrix B here. But the good thing here is that because this is really this Fx is not, it does not have partial information on the direction, does not have partial derivatives on different directions. So having discretizing the space will remain the Fx here to be a diagonal matrix where all the entry of the grid at x is going to be the function value Fx. So the part for simulation is this. So you can see such kind of Hamiltonian, I mean in the Hamiltonian, in the discrete space, it really has a very special structure. That the Laplacian term, it is probably going to be a little bit large, but it is independent of the function f here. So what is dependent on the f is a b, the matrix B here. But the matrix B here is a diagonal matrix, and actually, if you're familiar with previous quantum work on previous results on quantum simulation, diagonal matrices are very easy to be simulated. So in our work, we use a specific method from quantum simulation called a simulation under interaction picture in a recent paper due to Low and BF. It's just that for the interaction picture, it's very easy to manipulate between a term that is large and the other term being small, but easy to manipulate. So this, I think our work perfectly fits into the interaction picture. But actually, it turns out that the overall quantum quark complexity for simulating such kind of Schrodinger equation is called only like tilde O of like t times log n times like another log 2 term, log 2 term of the time. So this is really good, and actually finally we can put everything together. We put together the idea of using accelerated gradient descent, such kind of accelerated gradient descent idea, the idea of making the perturbation instead to replace of using quantum simulation to replace the classical perturbation, and also this idea of using quantum simulation for each step, like using the interaction picture idea to implement each simulation step. We can prove that we give a much faster convergence rate compared to the classical algorithm. Actually, if we replace, we put all like the logarithmic term together into something like this, like iota here. The iota here is only like to the second power. So actually only like a log n to the 2 here instead of classical algorithm has iota to the 6. So you see this is really a cubic quantum speed here. So I think let me just very briefly summarize the idea here. So the quantum algorithm here can be summarized into 4 points. So for the first point, as in the beginning of my talk, I mentioned this idea using like a quantum evaluation oracle to compute classical gradients. So similar to the convex, we just use Jordan's algorithm to compute each step of the gradient. And for the specific speed up in this work, is that we follow when the gradient is large, we just follow the classical way of using accelerated gradient descent. But when the gradient is small, we do something significantly faster, that we use quantum simulation with time O of log n, and we measure the outcome as the perturbation, like to replace the perturbation of the classical algorithms. And on the other hand, if we have and after making this kind of quantum simulation review, then further use a gradient descent for about log n iterations, and we depends on the case, we go back to step 2 or 3, and depending on the norm of the gradient. So as a summary, I'm going to draw a table here. So this is a very direct comparison between the classical and quantum algorithms. So classically, we are going to make a perturbation uniformly in a ball, but quantumly, we are just going to use quantum simulation. So for both algorithms, actually, after making the classical perturbation of the quantum or the quantum simulation, we are going to use still log n iterations for gradient descent. But you can see like they have some differences about like the cost of each step and also the function decrease. So classically, what makes everything very slow is that the function decrease is so small. It's only like 1 over log n to the 5. But quantumly, each step will decrease. If you assume epsilon to be a constant, the decrease is actually also a constant. So I'm probably not opening like the exact epsilon dependence here because it's a little bit complicated, but you can see like when we regard epsilon as a constant, like the dimension part of the quantum on the function increase is really much better. But quantum, we have to pay extra overhead in each step of the quantum simulation because there is a log n overhead. So in total, like classically, the cost is log n to the 6, and this is the reason why the quantum cost is log n to the 2. Okay, I guess this is going to be close to the end of my talk, but let me very briefly also highlight some numerical experiments. So we made quite a few different numerical experiments. For instance, we examined that actually the dispersion of the wave packet is valid. That basically we assume such kind of Gaussian wave packet. You can see it really actually going to disperse very fast like this on the most negative eigenvalue direction. And we also make a massive comparison between like the different. We also apply our quantum algorithm to quite a few different non-quadratic potential fields. So for instance, maybe like a landscape like this, and maybe like having such kind of circles, you can see that our quantum algorithm you can really see the dispersion along this direction. And actually, it is going to be getting quite close to the local minima here, and actually really solve the problem. And actually also on the other hand, maybe we want to consider some more difficult landscapes, maybe even something like maybe we have like a third order term and actually have such kind of like weird, maybe even a little bit weird contour figure, like maybe the height like this. So there's like a hill, there's like a ridge and valley, such kind of things like this. You can see they are really very nice, such kind of interference patterns of the quantum simulation. Actually, you can see that our quantum algorithm is really getting rid of these directions very fast. And also when comparing to the classical algorithms, the classical algorithm actually it is really going to, because this is the local minima and this is the set point. You can see like such kind of trees is what we want, and such kind of trees is really not something very good. And actually in our experiment, we can see that quantum is much better than the classical counterpart. And also for the dimensional dependence, the quantum algorithm is much better. So I think I'm probably going to run out of my time. So let me make a summary here. So the main conclusion is that for convex functions, we are going to give a fast quantum algorithm that is the cost roughly like 2 of n. And for non-convex function, our quantum algorithm is going to run with cost like log n to the 2 or epsilon to the 1.75. So compare to the classical state of the art respectively, for the convex optimization part, we achieve a quadratic quantum speedup, and for the non-convex optimization part, we achieve a cubic quantum speedup. And also maybe also highlight the technical contribution is that the 2 points is that we reduce classical gradient descent to quantum evaluations by the Jordan's algorithm, and also we use quantum simulation, this idea to escape from set of points. And possible open question is that, for instance, can we get quantum inspired classical algorithm for escaping from set of points? So the idea of our quantum algorithm probably says that this kind of escaping from set of points using like uniform perturbation is not the best. Maybe we want to use, for a quantum inspired classical algorithm is that we want to better utilize classical mechanics to not uniformly perturb, but maybe some other way, other perturbation that runs faster than the current log into the 6th classical algorithm. And also on the other hand, maybe you want to be more ambitious, that is beyond local minima, does quantum provide an advantage for approaching a global minima and actually can get more information or more ability to solve a corresponding optimization problem. So this is going to be the end of my talk, and thanks for your attention.
Thanks, TongYang, for the excellent talk. Before open to the audience in the Zoom, here's a question from the Bilibili. So let me read it. Okay. Sure. Actually, the question is related to your open problem 1. So compared to the classical optimization, the quantum speed up, is it mainly, so it can escape from the set point? Is it mainly because the quantum mechanics, I mean the quantum trick, the perturbation, or other reasons? Okay.
Yes, yes. I think this is a very nice question. I think the main point, as I mentioned during my talk, is this phenomenon of quantum tunneling. So I think we have this inspiration that maybe if we evolve some kind of quantum wave equation and can probably like escape from saddle points easier, and actually we observe the phenomenon and make everything algorithmic by the tools of quantum simulation. Yeah, I think I asked this question about like quantum-inspired classical algorithm for this topic. So this is basically something driven by quantum mechanics, but a very natural question is that can we think about some classical dynamics, maybe driven by some classical mechanics, like those from like Lagrangian mechanics, or maybe you use some clever ways, you have some clever ways of using mechanical waves, such that you can escape from the saddle point faster. I think during my talk I mentioned that this classical state of art due to Jin et al. Is like a uniform perturbation in a bell, but maybe you can utilize more information, maybe driven by some classical mechanics. You can also escape from saddle points faster than the current classical state of the art. I think this is a very important open question, not for the quantum field, but also for classical experts in learning theory.
Okay, related to your answer, I have another question. So
Sure.
here you use the gradient descent. We know that in classical, there's also the stochastic gradient descent. Yeah, so compared to that, so because there we also randomly pick a direction, and so how to compare your quantum algorithm with this?
Oh, that's a superb question. Yes, I think the point is this. In practice, I think stochastic gradient descent works better than perturbed gradient descent. So stochastic gradient, because for a lot of problems, it's just intrinsically have the structure of being stochasticity, and I think you can actually do things much faster. But I think from a theoretical analysis point of perspective, stochastic gradient descent is slower than the perturbed gradient descent, this kind of like non-stochastic version. So the currently state of the art result for the stochastic gradient descent for escaping from saddle points, I think is held by the Professor TongZhang's group. And I think the state of art is 1 over epsilon to the 3. So you see like the classical, like for the non-stochastic version is 1 over epsilon to the 3.25. So the stochastic version in practice, it works better, but theoretically, for non-stochastic versions, I think perturbed gradient descent works better. And that is also one of the most important reasons why we choose to quantize this algorithm.
Okay, so let me ask another question. So are there any lower bound?
Oh, that's a very good question. I don't know, actually. Yeah, I think classically the lower bound is even not very complete with the corresponding study. I think there are some non-trivial lower bound in terms of 1 over epsilon. So maybe the power, if I remember correctly, I think the classical, there is some lower bound, but the power is between 1 and 2, and it's not tight. It's not tight as to the 7 over 4 or this 1.75. Well, I think, yeah, quantumly, I'm currently not really counting on that because that sounds a little bit complicated, and I don't know how to show that, to be honest.
Okay, actually a related question. So may I ask, because you mentioned that you use some spirit of the quantum tunneling, I mean the Schrödinger equation. So so are there, I mean, it sounds like some magic. So do we have any method to prove lower bound for this type of thing?
I don't know, to be honest. Yeah, I think the main difficulty here is that I think most known quantum lower bounds, especially for instance, this result is like a quantum Kerr complexity result, but the previous quantum or classical Kerr complexity result really focuses on n instead of like the precision epsilon. So like the previous methods, like the polynomial method, like the adversary method, I think it does not directly applies to like the escaping from saddle points, nor like its specific methods like quantum simulation. Yeah, I don't have any clear clue, I think. Yeah, I don't know.
Okay. I think here's one more question from the Bilibili audience. Let me try to summarize it. I think the question is about the difference between the convex and the non-convex. So quantum, what's the key point here? The quantum speed up.
Yes. So this is also a very good question. I think convex optimization is more like a typical and classical problem, and it's a very good first point to study about. And I think classically, like previously literature, I mean, back to the long history, for instance, like the ellipsoid method, like the interior point method. Those kind of methods are very mature, and I think they're really trying to pushing forward along this line. But I think recently people have been focusing more and more on non-convex optimization. I think not only for its mathematical interest, but also because many, especially in machine learning, the vast majority of the models, I think their corresponding loss functions are non-convex. They're very non-convex, like the pictures I just showed. So speaking of the point about studying corresponding quantum algorithm for non-convex optimization, it's just like this. I mean, convex is something really regular, and classically there are more mature methods. But I think especially somehow, I mean, for more difficult problems, maybe you want to like count more on the quantum because maybe there are more magic from the quantum part. And especially after we have this kind of inspiration for tunneling, and the thing is, speaking of this kind of landscape, it's just like the convex function is just like one. Is this kind of it's just like it's very convex, and you only have like a unique local minimum, which is the global minimum. This really facilitates the corresponding study, but maybe and we hopefully that for some weird landscape and for some difficult landscape, we can bring more quantum speed up here. And as you can see that for the two results that actually we achieved, for the convex part, the speed up is quadratic, and non-convex part, the speed up is cubic. So I think this is actually more exciting for the non-convex part compared to the convex part.
Okay, thanks. So any questions from the room? Other audience from the Zoom room? Are there any questions? If no further question, let's thank TongYang again for the nice talk. Okay, thanks TongYang.